Hello everyone, my name is Keertiga and my teammate name is Danusha. We are excited to submit our project Distributed Close High Utility Items at Mining under the supervision of Dr. M.S. Bhuvaneshwari, Assistant Professor, Senior Grade in Department of Computer Science and Engineering. We chose this project because we wanted to harvest the closed high utility item set from the transaction databases. Closed high utility item set mining refers to the process of mining item sets with high utility when the items in the item set are sold together. So far, this procedure has been performed in a standalone manner. However, in order to achieve performance in terms of runtime and scalability, we have implemented in a distributed systems. We employ standard databases that are often used in the high utility items and mining literature. Each transaction in the retail dataset is now divided into three parts. The first section contains item IDs, then the second section contains transaction utility, and the third contains individual items utility. We use the datasets Chain Store, Foodmart, BMS, Pump SB, and Connect, which include similar information as retail. Now we are looking into the system design. The first module is to build the secondary set. The major goal of creating a secondary set is to avoid non-promising items in the transaction database and to narrow the search space. A utility measure known as local utility is utilized to create the secondary set. Each separate item's local utility is computed. Items with a greater local utility value than the minimum threshold are included into the secondary set. The resulting secondary set should be sorted in ascending order of the values of each item's local utility.
This is the output of the secondary set formation module. We have demonstrated each module by executing the detailed data set. The total number of transactions present in the detailed data set is 14,974 and the total number of distinct items is 3,468. And we have executed these modules by keeping the minimum utility threshold value as 1,50,000. After executing this module, the total number of items that are to be present in the secondary set have got us 2,650.
The second module is to build the projected database. The original transaction database is now entirely examined to eliminate any entries that are not present in the secondary set. The resulting database is a projected database with all items in each transaction sorted in ascending order of their local utility values.
And this is the output of the projected database construction. After pruning the items that are not present in the secondary set, the total number of transactions that are to be present in the projected database have got us 14,907. And this is the format of the output of the projected database construction.
The third module is to create a primary set. Items with subtree utility values larger than the provided threshold are combined to form a primary set. To accomplish this, we must compute the subtree utility values for each item in the projected database. In order to improve the performance, Tmap data structure that stores items and their accompanying transactions where they are present, allowing us to scan the transaction where the chosen item is present rather than scanning the entire projected database again and again.
And this is the output of this primary set formation. And this primary set is formed after computing the subtree utility. And here, as we all know, here we have taken the minimum utility threshold value as 1,50,000, and the items which have the subtree utility value greater than the minimum threshold value are taken to be present in the primary set, and the total number of items present in the primary set is 2,680.
And the final module will mine the CHUI from the previously examined search space. Backward extension is tested for each item set. If there is no backward extension, it is subjected to a closure jumping test. If the item set passes the closure jumping test, it is designated as a close high utility item set. Otherwise, the search space is furthermore explored. This procedure was performed for each item in the primary set. Finally, we will have a collection of close high utility item sets.
This is the output of the CHUA formation. and the total number of the close to high utility item set that have been generated for the retail data set is 6. Here we are executing the footmat data set in both the distributor system and the standalone system, and we are evaluating the execution time by varying the minimum utility threshold value. The execution time taken for executing the footman dataset in the distributor system is greater than that of the standalone system. This is because, as we all know, the distributor system is more suitable for the big data. So for the smaller number of transactions, standalone system seems to be better than the distributor system. We can compare this by executing the another dataset called the retail dataset. Retail dataset contains the transaction that are around 14,974. These transactions are greater when compared to the footmod dataset, and here also we are executing this for evaluating the uh, runtime by varying the threshold value, and here the time taken for the execution is greater in the standalone system than in the distributor system. This is because the retail dataset contains a more number of transactions, so it is efficient to execute this in the distributor system than in its standalone system.